So let me delve right in. As Mackenzie was alluding to, DeepLabCut falls into this bigger picture of software 2.0 that is really crucial for many, many applications, for like autonomous driving and things like that, all this modern AI stuff. And essentially what is new about this and why people call it software 2.0 is that you have an integration of annotation data, training, and inference in one platform. And in fact, the annotation data is really crucial to achieve the performance of these algorithms on the task of interest. And that's why you as a user are really crucial. And what you have been doing this week is you created projects, you extracted frames, and you labeled the body parts of interest for your particular problem. And of course, if you have those labeled frames, then the next step will be to split those labeled frames into two parts. They're often called the training and the test set. And the idea for that is that if you don't have a test set, because these algorithms are extremely powerful, you could be misled that they're working very well. So essentially, you really want to check if they actually work well on images that they weren't trained on. And that's what happens in this select and like make a train test split and then train your deep neural network. There's also some choice to what type of deep neural network you want to use, and we will discuss this a little bit. And then if you train your network, you want to evaluate it. That's also something we will talk about today a little bit. And if, let's say, it doesn't actually work well on some scenarios because the animals appear to be very different, for example, or various other reasons, they're unusual movements, then there's an active learning loop where you can basically identify frames where it doesn't work through heuristics or your visual impression, and then throw these images also into the training set, grow the training set, and therefore make a better network in that process. So that's what's called active learning. And this is something we will discuss next week. But if you have if you have the network working and you do not need to refine it because it actually works well, then you can use this network to run it on videos, to create, to do inference and to plot your results. And you can, for example, also share these networks with colleagues in your lab so that they can analyze their data if it's similar. Okay. So with that, let's delve right in. So as I said, we will really deal with selecting and training deep neural networks and then also the evaluation. And so with respect to training and selecting the training set, so there are quite a few choices. Namely, let me just list them. The choices with respect to what the network backbone is. In DeepLabCut, there are mobile nets, there are res nets, and there will be efficient nets coming out very soon. There's a choice to the scale. And these different things, as I will highlight next, have implications with regards to the inference speed and the training speed. And they have implications to what the precision is that you can expect from your network. And we will see that. And then for pre-training, so these are the backbones themselves. So that's just the architecture and how are the nodes in this neural network connected. And these features kind of have implications, as I highlighted, for performance. But what the specific weights are also choices. So one choice you could have, for example, is you could randomly initialize all the weights in your ResNet and then train, or you can actually initialize them in an ImageNet pre-trained fashion, where it actually is trained first on a different task, namely object recognition on a very large scale data set, and then is fine-tuned or via transfer learning onto your specific task. And that's what we call ImageNet pre-trained. And this is something you could call the generalist condition in DeepLabCut. That's the most recommended one. And that's also the case where we showed that you have short training times where you need little or relatively little training data and so on. So that is really recommended. But it could be that, let's say you work on human data and you actually work on humans standing upright. And in that case, it would make sense to, for example, start from a model that is pre-trained on human pose estimation, which is also in the model zoo. or other model zoo cases. Like say you work on dogs, then using the full dog model is actually kind of useful. And we'll discuss this a little bit going forward. And so these are kind of, that's the network, that's the initialization of the network weights. And then thirdly, what is also crucial is essentially how do you train it? So when you train neural networks, what happens is, so this is a supervised learning method. Your annotation data is the target of the algorithm. So in other words, for a given image that you have annotated, this image will be presented to the neural network, and your annotation data will be presented as the target essentially. And what the algorithm does in order to be trained is it takes the image and it forward predicts its prediction of where the body parts are. Then these predictions are compared to your labels. An error is calculated, and that error is back propagated through the whole network in order to update all the weights. And now specifically that can be done in many different ways. So firstly, how are the weights updated? There are different optimizers that can be used for this. Normally, this is also done in a stochastic gradient descent way. And for that, that means now that you actually calculate the gradient always on a given batch. So if you train, you either present, let's say, a single image and you forward predict and you compare it with the target and back propagate it, or you present multiple images simultaneously, that's a batch of larger than one, and you compare it to the targets. And if you have larger batches, then your estimation of the gradient is actually more reliable, and therefore the training is better. So that's something that is crucial. And another essential trick, and I will show this a little bit, is augmentation. Namely, if you think about it, if you, for example, annotate a given image with an animal, and if you slightly rotate this image, then probably if you also rotate your annotation, then that annotation of the image is also obviously correct. And what that means is there are actually very natural methods in which you can grow your training set without actually annotating more images. And that's something that is done during training automatically, and which is called augmentation transformations. So going forward, so the first thing I want to highlight is that for basically every convolutional neural network algorithm, the size of the image, so if you have here, for example, 320 by 240 pixels, and you consider ever smaller images, the size of the images fundamentally changes the speed of inference. So here what you see is the size versus the inference speed in frames per second. And this here is for batch size of 1. So you can notice that if you have very large frames, 554 square, then you get inference speeds. This is on the GPU of around 30 frames per second, and you can go up to 100 if you downsample. What we showed in this preprint here, or in this white paper, is actually that even if you downsample your spatial resolution, like the errors don't grow too dramatically. So in order to really analyze your data quickly, it does make sense to make the images, the videos, as small as possible. And this is, of course, just for batch size 1, which is, for example, useful for real-time feedback and processing. But what you should also do is you should actually do inference with larger batch sizes. And you can see this here. So for example, for this 80 by 60 video, if you use a batch size of 1, your inference speed is around 100. But if you use a batch size of 64, your inference speed is actually 450 frames per second. So it's way faster. And what you can also see is this final column here has data for CPUs. So it's not a GPU. And you see that the inference speeds are way slower than for the different GPUs that we tested here and benchmarked on different systems. So that's also why, for example, training on Colab and doing inference on Colab, where you actually get GPUs for free, is so much faster than, let's say, training and doing inference on your own laptop. That said, if in the lab, it's really recommended that you would get GPUs to take full advantage of DeepLabCut. And here, so this is all for the ResNet 50 backbone, but this figure here highlights the differences in different backbones. So here's a ResNet 50, which can have 50 layers, 101, 152, or different mobile nets. And what you see here, this line, for example, this is for video frame sizes of 512 by 512. This line here for different batch sizes refers to a ResNet 50. And if you use a ResNet with 101 layer, which is actually much more powerful, you obviously have a slower speed. But if you use, for example, these mobile nets, then you can dramatically increase your inference speed as well. And so here the question for you is essentially how much accuracy do you require, or do you care more about speed? And here you can see differences in accuracy. So namely what this is for a benchmarking data sets where we looked at different horses and pose estimation on horses. And what you see here is different architectures, namely different mobile nets and different ResNets. And you see the accuracy, so you see that basically their accuracy on solving object recognition is related to their accuracy for solving pose estimation. And better architectures, or more powerful architectures, are also more powerful on that specific problem. And interestingly also, they're even better on out of domain, so on unseen horses, they generalize way better than, let's say, the weakest mobile net. But at the same time, of course, mobile nets are much faster than the ResNets. And if, let's say, for you it would be sufficient to have an error of around 0.15, then it obviously would make sense to actually use a small mobile net. Okay. So in practice, how do you do this? When you create the training set in DeepLabCut create training set, you pass the configuration file, and here you can just set the net type, the network type that you want to use. And here this would be a mobile net that you are setting. There are lots of different architectures, as I highlighted, and you just have to pass this argument here. If you don't pass anything, then I think by default it will pick a ResNet 50. Okay. And then, as I said, these ResNet 50s or all these networks, they're just pre-trained on ImageNet, so they cannot do any pose estimation as such, a priori, without training them. But they're also completely configured. So in other words, these weights are just the weights that are within the backbone. But you can also share the weights at the readout here. And if you do that, then you can, of course, use the whole network to do pose estimation. And one example is in the model zoo is the MPI pose pre-trained model that is actually trained on 26,000 images of 50 or 40,000 humans. And in this case, when it's applied to a video of someone dancing in a bar, it just picks up the body parts, and it has never been trained on this. And similarly, and yeah, there's code to do this. And similarly, you can, of course, use the DeepLabCut models, and we will dig into this in a second, for lots of different other pre-trained models, namely cats, dogs, primate faces, for example, pupils. And there are many, many more models that will come. And we are actively seeking, and then, I mean, many of you are actually helping to expand these models and make them better by annotating additional data. So I also alluded to that it's really crucial to do augmentation, and different types of augmentation can strongly improve your performance. One example that we had is we have this case where cheetah is hunting, and these frames are extremely big, and the cheetah can be in lots of different locations. So one thing that makes sense here is to do automatic cropping, where you identify a random part of the cheetah, crop it out, and only train on that crop. And here you see that, for example, this method alone improves the accuracy by about twofold, actually. So this is a big difference. You're not annotating any more data, but just by making some smart selections of how it's trained, you get a much, much better network. So that's crucial. And here, these things highlight the different types of augmentations you can do. For example, you can add noise, you can do affine transformations, you can crop it and move it around, you can flip the orientation and so on. And this next image and this next slide is actually showing you how much better you can be with the loader. So on the left-hand side, this is the default loader that was introduced in DeepLabCut 2.0. And here's the performance for this loader, for this problem. And then here to the right, you see exactly the same data, but this is now trained with the ImageNet loader, the default parameters for this loader. And what you see is that you actually get almost twice as good especially on out-of-domain data with this loader. So this is highly recommended for different settings. Okay. Yeah. And again, when you create the training set, you can just pass what type of loader you want to use, and then you can take advantage of this. This is just to highlight the different parameters and how to set them and what they mean for these different loaders. And here, you see training curves where you see what will actually happen if you created your training split. What you see is that the cross entropy loss will change. Ideally, it goes down. If it actually doesn't go down, then there's probably an error in your annotation data. And it will go down, and at some point it kind of stabilizes and just slowly decays. If it slowly decays, you can essentially stop at any time. That's a natural stopping point. And the crucial thing, as I highlighted initially, you really don't care that much about the performance on training data, because these networks are so powerful, they can even memorize data. So what you really want to make sure is that they actually perform well on test data. Yeah. To be fair, sometimes it does make sense to look at training data, namely, especially if it doesn't work, like to fix an algorithm or something. But for you as a user, you really only care about test data. And you see here that after around, let's say, 50,000 iterations on test data, this network has already reached 3.5 pixel accuracy, and it keeps on decreasing until around 400,000 it actually reaches human level accuracy. Yeah. And this is an important thing, namely your noise level. So for example, the test and the training errors, they do not have to be the same. Usually they will never be the same, actually. But the test accuracy will usually approach something that is kind of the noise in your own labeling. And that makes sense, no? Because on the training set, that's something you give to the algorithm, so it will kind of overfit on that data. And that's something that these algorithms really do. So what you should do in order to figure out if the algorithm works for your case is, you should on the one hand really look at the test accuracy, and ideally even compare that to your own uncertainty. But most importantly, you should also plot the labels. And what you will, if you do that in DeepLabCut, what you'll get is images like this, where you have a cross, which is your original ground truth annotation, and then a dot, which is the DeepLabCut dot on top. And what you want to see on test images is that the prediction and the ground truth data is sufficiently close for what matters for your accuracy for the experiment you're doing. Okay, so obviously this would be a very good case. These are also good cases. Notice that in this case of the fly, there are some body parts that are occluded. Like in this case, we also annotate the left leg, and the left leg is obviously occluded and there's no ground truth for it. And it is actually this part in this violet, which means here you get a uncertain X, which is a prediction at that location, but it's indicated as an X because it's below the so-called P cutoff. And the P cutoff is really useful because it allows you to kind of automatically identify when body parts are occluded or not. So you should really make use of this, especially if you have cases where body parts can be occluded, okay? And what I should also say here is, for single animal DeepLabCut, the evaluation, I think, is relatively straightforward, and this basically covers everything. You just want to look at the test accuracy, you want to compare it to your noise level if you really care, and you want to look at the evaluation images. But in module 4, we can talk about evaluation for multi-animal projects, where there's actually some very important steps for cross-validating different parameters that we will discuss then.